All right, so I'm just going to change here. I'm just going to be doing it, typing up the information from the computer. We're asked, what do we notice about the coefficients of each expansion? So in this case, we know that the coefficients of the expansion are the same as values of rho n in Pascal's triangle. In this case, that would be rho 6, because our power up here is a plus b to the power of 6. What do you notice about the terms in the expansion of each binomial? So the actual terms themselves, we know that the degree of the first term, right? The degree of the first term is the same as the row number. The first term here is essentially the exponent a to the 0.
Good morning.
Right?
Can I have your attention, please, for one shower grace? Let's ask God to bless us now as we pray together.
All right, so what do we notice about the coefficients of each expansion? So the coefficients of the expansion are the same as the values of rho n in Pascal's triangle. So Pascal's triangle, rho 5 of Pascal's triangle is 1, 5, 10, 10, 5, 1. And those are the coefficients of our binomial expansion, 1, 5, 10, 10, 5, 1. Right? So we spoke about that. Last question. What do you notice about the terms in the expansion of each binomial? So there's a few things. The first is that the degree of each term is n. When I say the degree of the term, it's talking about the exponents of all the variables that are inside of it. So here we have a to the 5. Here we have a to the 4 and b to the 1. So 4 plus 1 is 5. That means this term is of degree 5. 10a to the cubed, b squared, 3 and 2 is 5. So all of the actual terms have a degree of 5. We also notice that the first term of the binomial has an exponent of n. So it's a plus b to the 5, a to the 5th. This is the first term, and it has an exponent of 5. And then every subsequent term, it decreases by 1. A5, A4, A3, A2, A1. And then, in fact, actually A0 here. A to the 0 is just the value of 1. Anything to the power of 0 is 1. So we don't bother writing it, but effectively it's A0. And then finally, we also notice that the second term of the binomial has a degree of 0 in the first term, and its degree increases by 1. So just as we said before, b, we don't see it listed in the...
Roberts, please dial 3402.
We don't see...
3402.
We don't see b listed in this first term, but we could write b to the power of 0. B to the power of 0 is just 1, so we don't bother writing it. And then it increases. B to the 1, b to the 2, b to the 3, b to the 4, b to the 5. All right? And then finally, the sum of all the exponents is n. That's effectively the same thing as saying the degree of each of these terms is n, because this exponent is 5. 4 plus 1 is 5. 3 plus 2 is 5. Well, the 3 plus 2, that's the exponent 3, b to the power of 2. That's what we're referring to as the degree of the term. So it's effectively saying the same thing. All right, so let's take a look at an example. So we'll apply this. Where's my screen shade? All right, so using choose notation, write the expansion of the following. When it says the word choose, it's really just meaning combinations. So a to the power of b squared is simply power 2. We have 2 items to choose. And so the first term becomes, we're choosing it as though we're choosing no items, 1 item, 2 items. And then our terms become a to the 2, a to the 1, a to the 0, and b does the opposite. B starts to the 0, then b to the 1, then b to the 2. That's all we need to do in order to answer this question. But if we were to expand what 2 choose 0 means, Pascal's triangle tells us that that's a 1. The coefficient is 2, and the coefficient is 1. So this shows us how we would expand it. But we are being asked to write it in choose notation, so we don't actually have to do this second part of the line. Here we have a to the power of b cubed. Again, our coefficients are going to be 3 because it's 3 cubed. So we have 3 items, of which we are choosing 0 in the first term. 3 items choose 1, 3 items choose 2, 3 items choose 3. And then the pattern becomes a cubed b0, a2, a1, a0. And then the b's are b0, b1, b2, b3. Pascal's triangle tells us the coefficients of the third row are 1, 3, 3, and 1. A plus b to the fourth, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. A to the fourth, b 0, decrease a by 1. A third is going to be 1b because I've got to make sure it's 3 plus 1, which gives me 4. A to the third, I'm now going to decrease by 1. A to the 2, and these have to add up to 4, so that must be b to the 2. 4, 3. A decreases by 1 again. I get a1, and I'm left with b3. And then finally, I have a to the 0, which is just 1, so I don't write it, and I'm left with b to the 4. So we can now generalize what is the binomial theorem. We can say that if we have a plus b to the power of n, that is going to be as though we have n items to choose from, and then our coefficients become n choose 0 plus n choose 1 plus n choose 2, and we continue dot, 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 all the way up until we have n choose n items. Those are the coefficients. Our variables, we take the first variable a, and that goes up to the power of n, and then that's going to subsequently decrease by 1. A to the n, a to the n minus 1, a to the n minus 2, all the way until we get a to the n minus n, or a to the 0. And then the second term, b, it starts off with b to the power of 0, and then b to the power of 1. Right? That 1 there is like we're choosing the 1 there. N minus 2, b2, all the way until we do a to the n minus n. We're subtracting n here, so now it's b to the power of n there. Here we subtracted 2, so then it was b to the 2. That's the general binomial theorem, how we expand a binomial. We can write these combinations because we're adding a series of terms. We can write this in sigma notation. Remember, sigma notation simply means the sum of terms. And I can see that my combinations go from an n choose 0 all the way up to an n choose n. So I'm going to start with my r equals 0 up until n, bracket, n items, choose r. So that n choose 0. The first time around, r would be 0. A to the n minus r is 0, so that would give me a to the n, b to the 0. A to the n, b to the 0. That's going to be my 0th term. On the next term, r is now 1, so that gives me n1, n1, n minus 1, n minus 1, r is 1, b1. So this is exactly the same as that. We should be familiar with both means of writing the binomial theorem, both in expanded form like so and using sigma notation. So we're now asked to give an example of how we would expand a plus b to the 8. The pattern is the exponent is 8, so it's 8 choose 0 all the way up to 8 choose 8. 8 choose 0, 8 choose 1, 8 choose 2, 8 choose 3, 8 choose 4, 8 choose 5, 8 choose 6, 8 choose 7, 8 choose 8. The exponents start off with a to the 8, b to the 0, we don't write. Then it's going to be a to the 7, b1, a to the 6, b2, a to the 5, b3, a to the 4, b4, a to the 3, b5, a to the 2, b6, a to the 1, b7, a to the 0, b8. And then it says simplify it algebraically and evaluate the coefficients using Pascal's triangle. Again, I'd refer back to my Pascal's triangle to get what the coefficients are. Coefficients are 1, 8, 28, 56, 70, 56, 28, 8, and 1 again. Sorry that you can't quite see what those are, but if you listen to what I just said, those are the correct terms, and you can also just refer to your Pascal's triangle. Another terrible copy here. 3x plus 2 to the 4th. This is going to be a little bit more complicated because we have a term that's 3x, not just x. So again, it's going to be, our coefficients are going to be 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And then the exponent is going to, this entire 3x is to the power of 4. 3x to the power of 3, and then 2 to the 1. 3x to the power of 2, 2 to the 2. 3x to the power of 3, 2 to the 1. And then 3x to the power of 0, we don't bother writing, so we're then left with 2 to the 4. If I expand that out, I should get the following answer: 81x fourth plus 216x cubed